Hello. So let us continue now with a new topic, and that is the introduction of the electric field. We're going to focus on the electric field of a single charge today. We're going to do then the dipole in the next lecture, and work towards a continuum, the electric field due to a continuum of charges, in the lecture after that. So this lecture is introducing a very broad concept of the field. Now this field idea we could have introduced last semester, but it is admittedly more abstract than what you were dealing with last semester and what we've been dealing with up to this point. Though I think after we deal with it for a little bit, it'll become more intuitive and feel more like second nature. And this concept of a field is used throughout physics. This semester we'll be thinking of it in terms of the electric and magnetic fields. The particle physicists, that are studying, fundamental particles, deal with a branch of physics called quantum field theory. Einstein's field equations are the equations that tell us how gravity operates in his theory of general relativity. And these are just some examples. So this idea of the field, at least the way that we are going to think about it, came about from Michael Faraday, who was not necessarily a very good mathematician, but he was very good at qualitatively and visually thinking about things in physics, which has a lot of importance and a lot of use, besides just being able to do a lot of fancy math. And this idea, though was not accepted at first, has stuck. So this idea, though, again, as it is usually the case, while his idea is kind of the formulation of what we now talk about today, there were kind of earlier ideas from Descartes, Kepler, and others that had this idea of the field resulting from electric charges, magnetism, and other things. Let me provide some motivation of what we're going to talk about here. Again, and we can take gravity as an example to start with. I have a ball, and I throw the ball into the air, and I think we would all agree that the ball might ascend for a little bit, but it would slow down, stop, and eventually fall back towards the earth. And we could ask ourselves, why is it falling back towards the earth? And you would say, gravity. I would say, gravity of what? You would say the earth is pulling on the ball. Okay? Good. So then I would say, is there a force? You would say, yes, there's a force, a gravitational force. And if I'm near the surface of the earth, it's a gravitational force such that the mass of the ball times 9.8 meters per second squared is the magnitude of the force. And if you're far away from the surface of the earth, then you have to use the more general gmm over r squared. I would say, fine, that's all well and good. That's describing and giving the magnitude and direction of forces. But forces, particularly, as was kind of described and detailed by Newton, involves interactions. And we've talked about this in class, how forces arise because of interactions. I push on the box. I'm touching the box and therefore exert a force on the box. I throw the ball into the air. The ball is moving because of a force I exerted on it, which then ceases to exist once the ball and my hand lose contact. Forces are the result of interactions. So you could think then, what is going on with gravity? If I throw a ball into the air, you would all agree that there's a gravitational force acting on the ball, yet the ball is not necessarily touching the earth at that point. When it's in the air, it is definitely not touching the earth. And so the earth is somehow reaching across space and touching and doing something that you might think has to do with touching the ball if forces arise because of interactions. You might say, okay, well, maybe the earth and the atmosphere, or maybe there's some transitive thing going on. Fine. That'd be a model, that one could design experiments and test. But then how about we take the sun and the earth? The earth orbits the sun because of the sun's gravitational force on the earth. And we can treat space as a pretty dang good vacuum. So in that case, there is no kind of intermediary medium that this force might be exerted throughout. So what's going on there? This gives a rise to this idea of action at a distance, which the idea of gravity is some sort of force that does not require two things to be touching in order for that force to exist. The force appears to be somehow reaching across space in order to interact with the object. We've seen this now in this class as well, the electrostatic force. I have two charges that are not touching, and yet they are interacting with one another and exert a force. And we have calculated that force now for a couple days now. This idea of action at a distance troubled a lot of people, including Newton. This idea that you could have things not touching and yet exerting forces on one another. And again, let's motivate this again with two charges. I have QA located here, and I have QB located here. We have talked about how the force they exert on each other must point somewhere along the line connecting the two. And in the case of them being two positive charges, the force on A from B points away from charge B in this direction. Its magnitude is given by the Coulomb law of force. K, the product of the charges, divided by the square of the distance between them, where we define this vectorially as this vector points to A from B. Then if I move that charge A and move here instead, so now here's where Q sub A is, then there is still a force exerted on Q sub A as a result of Q sub B and Q sub A, and it's pointing in this direction. And its magnitude is different, depending on if the charges are different and the fact that the distance between them has changed. But again, they are not touching one another. So what's going on? We could ask some other questions that really troubled people, really troubled Einstein as well. Suppose you place Q sub A first. Then at some time later, you place Q sub B. We would agree that Q sub A would then feel a force from Q sub B. Now, does Q sub A feel this force? Right, so we'll call it F on A from B. Does it feel this force instantly? Does it feel it, after some delay? If I place Q sub B down, does Q sub A immediately feel the presence of that Q sub B? Or does it take some time for Q sub A to kind of become aware that Q sub B is there? If you're thinking instantly, well, then let's do the thought experiment of I have Q sub A located here on campus, and then Q sub B is a charge that I place over in the Andromeda galaxy. This thing is hundreds of thousands of light years away. Are we saying that the charge here in Moraga feels that force immediately or after a delay? So this also gets us into the idea of approximations. So for us, we're going to say that it happens instantly. Though in reality, that is not what happens. In reality, there is a delay, but this delay is set by the speed of light. Which we usually use the symbol c for the speed of light, is approximately 3 times 10 to the 8 meters per second, or about 186,000 miles per second. 186,000, not miles per hour, miles per second, which is pretty fast. So the delay is set by essentially this information, if you want to think of it as that, the information that Q sub B is there propagates outward at the speed of light. And since the distances that we're dealing with in this course are pretty small, it's as if it was essentially instantaneous. And suppose I have two charges separated by a meter. Well, then what I'm saying is that if a Q is placed here, it propagates that information out at the speed of light. And so then, it's Q sub B, when does Q sub A become aware? When that information gets to it. Essentially receives a telegram saying, hey, there's a charge located 1 meter away to the right. So how long does this take? Well, that's a pretty simple formula. The speed of light being a constant, t equals the speed of light times delta t, and delta t, which is going to be d over c, 1 meter over 3 times 10 to the 8 meters per second. The meters cancel, the 1 over seconds flips around, and this becomes 1/3 times 10 to the minus 8 seconds. Or if I kind of force factor and yank out a 10, well, yanking out a 10 actually makes this 10 to the minus 9 divided by 3 seconds, which then that becomes 3.3 times 10 to the minus 9 seconds, or 3.3 nanoseconds. It takes about 3.3 nanoseconds for light to travel about a meter. So if you're 6 feet tall, you're approximately 2 meters tall, a beam of light goes from your head to your toes in about 6.5 seconds or so. 6.5 nanoseconds or so. That's pretty fast. And then this becomes even smaller if we're dealing with, say, you have an electron that's kind of existing around a nucleus. We'll just use hydrogen, for example, because the charge doesn't matter, but this distance here is something like 10 to the minus 10 meters. So then this delta t just becomes 10 to the minus 10 times as small. So it becomes 3.3 times 10 to the minus 10 times 10 to the minus 9 seconds, or about 3.3 times 10 to the minus 19 seconds, which is really, really fast. Hard to even know how you might measure that without very, very fancy equipment. So in this case, we can approximate that this information is known instantaneously. And that is essentially what Newtonian physics is doing. It is approximating this information speed as being instantaneously known. Now, that's an approximation which we will use for the rest of the semester, and that will be perfectly well and good for what we're trying to do. It's only when we have to when we start to butt up against the limits of this approximation that we have to start to be careful. And I just want to kind of give let me go over. It's kind of a small digression, if you'll allow me, of just kind of an overview of physics. We are working in this course kind of in the realm of classical mechanics, or you might call it Newtonian mechanics. This, of course, was the kind of original branch of physics that, Newton's laws, these kind of early ideas of fields, that were all well and good until people realized, when they started to push the limits of these theories, these models, that they were starting to get answers that did not agree with observations. In which case, then, that motivated new branches of physics to be developed. Particularly in the case of the field, this, the ideas of electromagnetism motivated the idea of what is the kind of origin of the field, what causes the field, how does this information propagate, just like what we were talking about. So there's 3 axes, really, that we can think about in terms of all of physics. This axis that goes this way, you can think of this as the speed axis. So what happens when you start to move things faster and faster and faster, particularly when you approach the speed of light. Well then, Newtonian physics starts to give you the wrong answer. Therefore, new physics had to be developed, or new models of physics had to be developed, models of physics that should give you a more accurate prediction when you are moving very fast, i.e. close to the speed of light, but who, in the limit where you're not moving that fast, should still give you the same answer that classical physics was giving. Because classical physics, if it's making accurate predictions, we should be able to reproduce those predictions in other branches and other kind of models of physics. So this is then what is kind of called special relativity, which allows you to explain what's going on when things are moving very fast, i.e. close to the speed of light. This then gives ideas of how, say, these fields propagate in things that we will not deal with in this semester, but is kind of useful if you want to do a more sophisticated formulation of these topics. There's also the realizations that happened in the 20th century that as you go to smaller and smaller sizes, and so we'll have another axis here, which, in going to the right, we kind of increased in speed. Here I'm trying to decrease in size. So, and I want the arrows to point in a specific way. So I'm going to call this axis 1 over size. So as size gets big, 1 over size is small, and that gets us back to classical mechanics. As I follow the arrow, because the arrows usually point in the way where the thing gets bigger, then that means size is getting smaller and smaller and smaller. You then get to a branch of physics, which is quantum mechanics. Which can be used to figure out what's going on inside those atoms and all that sort. Then, been very successful at kind of combining these two. So along the axis where you are moving very fast, we have the speed axis, and you are also doing things that are very, very small. So that's what's known as quantum field theory. Now, there's a third axis to think about, which I will have it kind of branch out of the page. And this is going to be the gravity axis. So, this is going to be the axis that deals with, you can think of it in terms of like, I'm thinking about the strength of gravity, which seems to behave differently than the other fundamental forces. We have kind of been successful at unifying the 3 of the 4 fundamental forces, which are the nuclear forces and electromagnetism. We can figure out how all of those kind of work together. Gravity seems to be kind of the holdout, so we give it its own axis for now. And so there's this branch of physics here, which is then general relativity. And this axis, if you want to think of it, so essentially we have the speed axis, which is dealing with the constant c, the speed of light. As v approaches the speed of light, that is u moving to the right. There is the size axis, which deals with the constant h, which is known as Planck's constant, which is kind of the constant that flies around in your equations whenever you're dealing with quantum physics. Just how c appears when you're dealing with relativity, and how capital G appears when you're dealing with gravity. Now, the gravity you might think of as yeah, essentially the way it's sometimes framed is it just uses capital G, but I might just call it G kind of m over c squared, where you're kind of you're dealing with gravity. That's the presence of big G, but it's the kind of the gravity resulting from kind of mass or energy, which is why this is also not perfect. Which then also deals with the speed of light, right? Thinking of mc squared. This value here ends up having units of length, and is actually 1/2 what's called the Schwarzschild radius, which you might have heard about in terms of black holes, the size of black holes. So essentially, what but for right now, I'll just kind of frame it as capital G. So essentially, general relativity is dealing with, we've moved over to the right, so we were dealing potentially with high speeds, particularly because we are now dealing with fields. And on this gravity axis, we're dealing with distortions, since Einstein's theory of general relativity is telling us that space-time is curved as the result of mass or energy. Excuse me. We seem to get the hiccups when I do this. That general relativity is dealing with the distortions of space and time from the result of mass or energy. So, now, what we have not been successful at doing yet is, maybe I'll actually make it a different color, is all arrows are pointing to kind of this one final location where it's kind of the intersection of all three axes, where you are dealing with potentially high speeds, you're dealing with things on very small size scales, and you might also be dealing with distortions that can be extreme warps and curvature due to, say, a large amount of mass or a large amount of energy. And this is what's called the kind of theory of everything, which, as of now, is we have been unable to kind of model. So what's going on here is that while this class is essentially sticking over here, the way to think of it is that not that everything we're doing is completely wrong, but what we're doing is a very valid approximation as long as we know our limitations. If we try to start moving things close to the speed of light, then we need to revert over to relativity. If we start to deal with things that are very, very small, then we need to revert over to quantum mechanics. If we're dealing with both, that gives us quantum field theory. If we're dealing with fast things that have a lot of mass or a lot of energy, that's general relativity. And then all of those are presumably some approximation of some grander, more quote-unquote correct theory, which we call the theory of everything, where all of these must be some approximation of that. So, and again, this is why, on your first day of Physics 1, we did not start with Einstein's field equations or the equations of, or Schrödinger's equations of quantum mechanics. While those are we believe, more accurate representations of nature, working with just Newton's laws in classical mechanics does perfectly well to kind of ground us, in the subject, and then as we become more sophisticated, we can branch into these other fields. And then, as the practitioners hope to do, kind of take that body of knowledge and go even farther to this theory of everything. So essentially in this class, we are making the approximation, so kind of classical mechanics. We're essentially making the approximation that the speed of light is infinite. So essentially information propagates instantaneously. h goes to 0, so we're not essentially dealing with quantum mechanics. And then g essentially goes to 0, but we'll just say that g goes to, you might think of it as kind of like gmm over c squared, or gm over c squared is very, very small. So as long as we're not, say, trying to do physics inside a black hole, then we do not need to move over to general relativity, for example. We can still have gravity. We can still have Newtonian gravity, which is why I don't want to write g equals 0, or g goes to 0. Really what we're doing is that we're making some approximations. Okay. End of digression. So, let's see, how do we introduce this concept of the field? What we want to do is we want to think about, right, you have your system and your agent. The system feels a force from an agent. Something that exists outside the system that is interacting with it. Maybe it's a direct push. Maybe it's now this idea of action at a distance, that we're going to essentially provide a liaison, or essentially a new agent called the field. So let's think of what's going on. So let's suppose I have Q sub b located here. And then if I were to place Q sub a at this location, now that's where we're going to place Q sub a. Again, we would agree that the force exists somewhere along that line. And this kind of, oops, not dotted, this line here, or this vector here that connects the two is r. And this I'm going to just have be the location of Q sub a. If I were to place Q sub a there, then we could determine the direction of the force. And the idea is that if we have Q, where the force on A from B is, again, K, QA, QB, square of the distance between them in the direction r hat, where r is defined as RA minus RB. Now, if I want to think about this in terms of systems and agents, let's think about the agent. Essentially, I want to try to take this force equation. The way I'm going to frame it is I want to try to take this force equation and I want to try to separate out the system and the agent. So I want to try to lump essentially anything that has to do with the system here, and then anything that has to do with the agent here. And again, the idea here is that we're trying to think about how the agent interacts with the system, which we're going to use this concept called the field. So let's think about this a little bit. Now, in the way I've drawn it on the right, that's the location of Q sub a, and then essentially if I know that the location of Q sub a is going to be there, I know the vector r, I know the distance between these two locations, I know the charge Q sub b, and at that point the only thing that needs to be provided is Q sub a, and then that will tell me the direction and magnitude of the force. I could also put this as the location. Suppose I want to say that, location of Q sub a. In which case, then we know that this becomes the vector r. And if I know that's going to be the location, then I know r, I know the vector r, because I could figure out the distance between the two. I have q sub b, and I only then need to know q sub a, and that will tell me the force. I could imagine doing that for every single location that is not q sub b. So I can imagine doing it here, 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 and here, and here, and I think you get the idea. That at every single point in space, I could figure out the distance to that location from q sub b, and I would have the charge q sub b, and the only thing I would need is that you would need to tell me what q sub a is, and at that location I would tell you the direction and magnitude of the force. So, let's define the electric field. I'm going to be more explicit. I'm going to say the electric field of q sub b as, so this electric field, which I'll use capital E, is going to be defined as the force on A from B divided by q sub A. Essentially the idea of, I know if I had two charges, I would know and I would know the separation between them, and I know the charges, I can figure out this force. I'm essentially dividing out by that charge, q sub A. That then leaves me with something that does not depend on q sub A, because the q sub A cancels out in this case, and essentially is completely independent of what q sub A is and what that charge is. And tells me something, so I could just write this down, K, q sub b, r hat. But then I might write r as r, and essentially I've divided out by the a, so I'm going to just put my little dotted circle there, minus rb. And that this quantity, E, only depends on properties of q sub b. It only depends on the charge q sub b. And this quantity is defined as a vector field defined everywhere in space. Now if we go back up to our drawing, I could think about how I might draw this thing. I'll use a different color here. So let's start with this location here. So at this location, I know that if I were to, and let's take q sub b to be positive for right now. All right, so then let's make that assumption more clear. Q sub b is positive. That at, say, this location, if I want to look at the electric field, then it seems like it points, I know that r points to this location from q sub b. So this arrow is still exactly the same, because it points to this location from q sub b. So that's r hat. That defines the direction of r hat, points in this direction. And then it depends on the charge q sub b, so that if q sub b is positive, there's no overall negative sign. In that case, that suggests that the electric field points away from q sub b. At this point up here, similarly, the electric field points away from q sub b in that direction. This location, just trying to get the idea. This quantity here is saying essentially it is encapsulating everything you need to know about q sub b, that if I were to place a charge at those hypothetical locations, I could then calculate the force. So another way to write this is that we can write it the force on A from B is equal to Q sub A times the electric field from B, or of Q sub B. So this only deals with Q sub B, and then Q sub A is separated, such that this then is the system, and this becomes the agent. This field is essentially the way of Q sub B letting itself be known to the cosmos. It then essentially has sent out this message, which is encoded in the electric field, so that if any other charges wander through this electric field, they know how to translate the presence of Q sub B into a force. And if the charge is negative, if Q sub B is negative, then it's the opposite. I'll actually redraw it. So let's see, let's have Q sub B. Then over here I'll have Q sub B less than 0. So some negative charge, and here I'll have a positive charge. Then, directly above, then maybe kind of 45-degree diagonal down below. So for a positive charge, this shows by the formula that the electric field from B points away. In this case, the electric field, since the Q, see going back up here, if the Q is then overall has a negative sign, then while this R vector, again, here to here, that is R. Oops, sorry, wrong. Well, that is true. I guess I can keep it. I was meant to do the other diagram. Right, that is R, the direction that points to that spot from Q sub B. But since Q sub B is negative, then the direction is flipped. Similarly, direction is flipped, which pops out just from the kind of vector description in the math of it all. So we then have kind of conceptually, one thing to point out is that E sub B points away from Q sub B if Q sub B is. So I apologize that the connection between my iPad and my computer broke, and I did not realize it for a few minutes. So let me kind of recap kind of what I was saying, though I've edited out the part where you were just staring at a blank screen. So again, the idea here is that if I have a positive charge, it is a distance r away from this hypothetical point, and with a positive charge, the electric field points away at that location. At this location, the vector r is now this, and for a positive charge, the electric field due to B, Q sub B, points away. Similarly, if I have the same, if I have the identical setup, but this Q sub B is negative, the electric field points towards Q sub B in both cases. So, conceptually, the idea is that by the way we have written it down, and this is borne out entirely with the formula here, that when the charge is positive, the electric field points away from that charge, just like what we saw here, and kind of like what I was drawing up here. Here the electric field always points away. The electric field of Q sub B points away from Q sub B. And then, if Q sub B is negative, then it's the same formula, but then this quantity here has a negative sign flying around. That negative sign then flips the direction of the vector, so then it points towards. Both cases, the magnitude is still given by kq sub b over r squared. And since magnitudes are technically always positive, right, I threw an absolute value sign there, where again, r is the vector that points to this location from q sub b. And geometrically, again, this is just a vector that points to a location from q sub b. The fact that I've drawn, there's no a here, and it's now this kind of dotted circle. The reason is because this is what's, again, called a vector field, which is defined at every point in space. So, showing you some pictures from the book. For the positive charge, at any point I could define an electric field that is this central charge's telegram to the world of its presence, and then that can get transcribed into a force if a charge then is located nearby. So at this location here, if this is q sub b, then at these points here, notice we've drawn vectors that are pointing away, and they're all the same length because they're all the same distance away from that central charge. These points here are the arrows are all pointing away, but they are farther away than the other 4 points. These 4 points is some distance away, but then again by the Pythagorean theorem we know these points here are slightly farther away than the other 4, and so I've drawn the vector magnitude to be decreased. And similarly at these points here, which seem to exist kind of along a circle of some larger radius, all the arrows point away, and I've reduced the magnitude by showing a slightly smaller arrow. So again, these arrows are specifying the electric field from this q sub b at every point in space. And similarly, this is the electric field from q sub b. In this case, the charge is now negative. And notice all that has done is flipped the direction of the arrows. This thing on the right is just kind of showing you that the notation used in the book is ever so slightly different than what I am using, but it is saying the same thing. So, this is different than, say, a force vectors. When we wrote down a force vector, say q sub a, f of a on a from b, right? That is only defined between 2 specific points. You have q sub a, I have q sub b, and I can draw an arrow for this force vector. And I only can draw one arrow for this force, right? The force on a from b. Where the idea of a vector field is that I can have arrows drawn everywhere. Again, just like the drawings above. I can draw arrows everywhere depending on how far away I am from that charge, for example, and whether the charge is positive or negative. These vector fields are seen in other contexts as well. So if you're thinking of, if I wanted to describe, the direction of wind, across a city, I might have vector arrows, overplotted on top of a city map, that shows what's going on there, or water flow. If you can think of just like water flowing through a pipe, you can imagine I could draw arrows that represents the speed of the water at particular locations. I'll just do a quick drawing here. Right, I have a pipe that maybe diverges. So at every point I might have arrows that that specify the speed and direction of, say, the water in the pipe, for example. So these vector fields are quite useful, but it's a little bit more abstract compared to a force vector, which requires 2 objects. Here we're taking just one object and ascribing a field everywhere. And I think you're also starting to see that if I were to describe this kind of geometrically, that these fields for a single charge are radial. So I made a couple little simple animations showing this in Mathematica. So, if this were a positive charge, so I'm kind of assuming that it's a positive charge, notice that then, if this represents the electric field, all the electric field lines are pointing directly away. Now you might say they all look the same length. And so, yes, typically when we're doing these sorts of visualizations, the graph becomes very, very cumbersome and very, very busy if we have a bunch of arrows that are all different lengths. So usually what we do is that we draw all the arrows to be the same length, but then we have a color that's associated with the magnitude. So in this case, kind of yellows and bright colors are large magnitudes, where these darks correspond to small magnitudes. And I'm just showing this to be kind of qualitative, not necessarily quantitative. But then the idea, of course, is that if I move the charge, notice that the arrows adjust themselves accordingly in terms of the direction of the electric field. And then if I flip the charge to have it be negative, the arrows then switch directions. So that points away from positive charges and towards negative charges. I might also be interested, let me reset it. I might also be interested in thinking about at what locations is the magnitude of the electric field the same value? Like, again, I'm not giving you enough information here to actually calculate numbers, but suppose I ask, where is the electric field all equal to 1, or a half, or 10? I can make these contours, which are essentially showing 1, I think it's 0.9, 0.8, 0.7, and 0.6. And so unsurprisingly, you can see that they're kind of circular, which makes sense because it only depends on kind of the distance between this Q sub B and this hypothetical location. Pick any point along the circle, and all those points are the same distance away from that central Q charge. Therefore, the evaluation of the magnitude of the electric field is always going to be the same anywhere along that circle. And then pick a different circle anywhere along that circle location is going to have the same magnitude of the electric field. Now notice how they're not evenly spaced apart. They're kind of scrunched together and they get spread farther and farther apart. Well, that you're just seeing the inverse square law. That as I get farther and farther away, and I can go back to kind of this, the inverse square law, if I were to plot it, that of course looks something like this. So that in order for the value to drop, say, by a half, the spacing between the contours gets spread more and more farther apart. And we'll see that in the following chapters when we go to electric potential as well. Of course, these things are three-dimensional, which becomes even harder to visualize. So you can imagine some sort of positive charge, and then you have field lines that can, again, point away from the positive charge, which can be, depending on the location of the charge, to dictate what direction they point. If it's negative, of course, it's flipped. And therefore, instead of drawing circles where the magnitude is all the same, you can imagine drawing spheres where the magnitude of the electric field is all the same. For this lecture, we're just sticking with a single charge. So let me see what we want to do. I want to do one quantitative problem for sure, but let's do this, and I'll put the other problem I had in mind on the sheet we do in class. So suppose I have Q sub B, and then I have, along this horizontal line, there's going to be some hypothetical, there's going to be some location here, which is where I'm going to ultimately place a charge. And the questions I'm going to ask is, given what is drawn, can you draw the electric field from B? Can you draw the force on A from B? Or is more information needed? So I'm ultimately going to place a charge there, but I have not placed it yet. So in this case, I'm going to need this drawing a couple times. Let me make some copies. So in this case, this first drawing, can I draw the electric field at that location from Q sub B? Yes, I can. If Q sub B is taken to be positive, then I can draw the electric field. I know it's going to point away, and it's going to have some magnitude depending on, that's going to depend on, say, the distance between the 2 points and the charge Q sub B. If I now have the setup, but now I have, let's now place Q sub A, which is also positive. What can I draw? And does anything in the previous drawing change? Well, this is still the same R, and therefore the electric field is still the same. So you need to be able to see. Yeah, so I'll draw the same arrow. Q sub B. The electric field does not change at all, because the electric field only has to do with what's going on with Q sub B. It doesn't care what Q sub A is. However, now that Q sub A is there, I can draw a force, which maybe it has this length. Maybe that's force Q sub A, force on A from B, which again is Q sub A multiplied by this vector EB. Now what about the setup where I have Q sub A again, but it's negative? What changes then? Well, again, E sub B does not care about what Q sub A is, so E sub B still points away, because E sub B is dealing entirely with Q sub B. But then once Q sub A is there, I know then that the force vector is going to point in the opposite direction. In this case, we'll have the same magnitude. But since it's negative, the force vector is going to flip signs, or flip directions, because of that change in sign. And then last but not least, same setup. Let me now do Q sub A. Let me go back to it being positive. But if Q sub A always was the same charge in the previous ones, maybe this is 2 times Q sub A. So twice as much charge. So what's changed? Well, again, this R vector has not changed. And therefore, this E vector, and I have not changed anything but Q sub B, and this E vector is still going to be the same. But the force vector, once I multiply by this charge to Q sub A, is going to then be twice as long. So then that's going to be the force on A from B. Guess I still need one more. I wonder if it's saved in my clipboard. Probably not. No. Naturally. Alright, let's see which one is. Can I copy? Then, once more with feeling. I erase this. Now let's do the case where Q sub B's charge changes in magnitude. So now, suppose I have 2 Q sub B. This is back to the original Q sub A, greater than 0. which is supposed to be red. Now it changes. Well, Q sub B is still positive. It's now just twice as big. So the electric field now is twice as big at that location. And then I'm going to take that and multiply it by Q sub A. So if I go back to the original vector, up top for the force, that has to be twice as long. So it looks like then this is going to be essentially this again, F A from B. And then you can try doing it like, what if Q sub B becomes negative? Which of these change? These are good conceptual questions to think about, right? Flip the sign of Q sub B and see how and try to imagine how all of these change. Which flip, which don't. Do any change length if I just flip the sign of Q sub B? Or what if I change both Q sub A and Q sub B to be twice as big? What changes? Good things to test yourself on. All right. And then let's do one quantitative problem and call it. So let's imagine a square where each side has a length of 1 centimeter, or 10 to the minus 2 meters. And I want to know, and then there's this charge Q sub B down here, which has a charge of, let's say negative 1 nanocoulomb, or negative 10 to the negative 9 coulombs. And I would like to know, what is the electric field at this location? And what is the electric field at that location? So we'll call this location 1 and this location 2. So for location 1, E sub B is going to be K Q sub B over the distance between that location and Q sub B squared, and then it's R hat, where R is the distance or the position vector to that location minus the position vector to R sub B. Now, I need to throw down a coordinate system if I want to be quantitative about this, which means I get to select a location for my origin and a location for the x and the y directions. Of course, I will be sane, and I will have the x direction be this way, and the y direction be this way. And I'm going to put my origin, because again, I can put my origin wherever I want. I'm going to put the origin at Q sub B. So, do I have to put the origin there? No. But this will at least make my life easier. So in that case, then I guess everything I've written down is general. It's not just true for position 1. So for position 1, then this location looks like it is just up 1 centimeter from the origin. So it looks like that is 10 to the minus 2 meters in the y direction. Or if you like column vectors, 0, 10 to the minus 2 meters. Then, again, the nice thing is that R sub B is 0, or it's the null vector. So then R is the same thing as the vector to this location. Again, that's what helps make my life easy. The magnitude is then just 10 to the minus 2 meters. So therefore the unit vector is going to be 1 over 10 to the minus 2 meters multiplied by the original vector, 10 to the minus 2 meters, times y hat, which of course then just becomes y hat, which makes sense. the direction that goes from Q sub B to this location is just up. If you go on a column vector, 0, 1. And now we put it all together. So then E is K Q sub B, this distance squared, r hat, which K, I'm going to round to 9 times 10 to the 9. In SI units, I've converted the Q and the R to SI units, so I know that ultimately this better have SI, the units better work out. I guess maybe I should state before we do this. I was going to do it at the end of the example, but let's state now. Go back up here. What is the units of the electric field? Well, if you look to the original equation, it looks like that is going to, it better have the same units as F divided by the unit of charge. The unit of F is newtons, the unit of charge is coulombs, the unit of the electric field is newtons per coulomb, given what we have done already. You'll also see it's defined as volts per meter, but we have not gotten there yet. So then, if I write everything in terms of SI units, I know that ultimately the answer is going to be newtons per coulomb. So then I have K, 9 times 10 to the 9, the negative 1 nanocoulomb. Oh my god, it broke again. At least I caught it this time. So we're just going to do this in real time, because I'm not going to edit this video anymore. I do not know why it is just not cooperating tonight. Especially when we're so close to being done. Come on, come back. All right. Gotta push through. All right. Divide by the distance between them squared. So it's 10 to the minus 2 squared times r hat, which we said r hat was just y hat. So then, what does that become? Looks like it becomes negative 9 times 10 to the 9 times 10 to the minus 9 divided by 10 to the minus 4. And that looks like then it becomes negative 9 times 10 to the 4 Newton. I forgot the y hat. Y hat, where it looks like it is 9 times 10 to the 4 newtons per coulomb. And then there's this negative y hat. Could I have left the negative sign up front? Absolutely. But in this case, then I can again see that this is the magnitude, 90,000, and the direction, which points down. Now, does that make sense? We said that the electric field points away from positive charges and towards negative charges, and it looks like this is indeed pointing towards the charge in the lower left corner. So, the electric field here looks like it is indeed pointing down. Now, of course, we could have qualitatively argued that, as we should. Like for the next example, we know that it better point kind of diagonally down, towards that charge. Let's now see. Yeah, that's fine. It's kind of not on the same page for me, but easy for you to look back in your notes. So then for 2, I guess I do need the drawing. Here's Q sub B, and here's the hypothetical location. And this is a square of 1 centimeter by 1 centimeter. So I need this vector, this R, which in the previous example we said is just the same thing as the position vector to this location. Since I put my origin at Q sub B, I could even draw axes kind of like there, so I know that my origin is there. So in this case, what is this vector? Well, it looks like the hypotenuse of a triangle. I could think geometrically. Looks like there's a triangle here. That's all good if I want to think of it that way. Or since I want to think of it as a vector, this vector is the same as if I started at the origin, went over a centimeter, and then went up a centimeter. So this is the same as 10 to the minus 2 meters in the x direction, and I go up 10 to the minus 2 meters in the y direction. Or, if you want like columns, 10 to the minus 2, 10 to the minus 2 meters. The magnitude is then just, by the Pythagorean theorem, square root of 2 times 10 to the minus 2 meters. And therefore, r hat is 1 over the square root of 10 to the minus 2 multiplied by the original vector, 10 to the minus 2, 10 to the minus 2. So it looks like it is 1 over the square root of 2, 1, 1, or 1 over the square root of 2, comma, 1 over the square root of 2, if you like column vectors, or 1 over the square root of 2, x hat plus y hat. And then, again, we put it all together. The electric field is 9 times 10 to the 9 times negative 10 to the minus 9 coulombs all over this distance, square root of 2 times 10 to the minus 2, all squared. And then r hat, we said, was 1 over root 2, 1 over root 2. And how does this simplify? The 10 to the 9s cancel out again. Looks like I have 9 on top. All over the square root of 2 squared becomes 2. 10 to the minus 2 squared becomes 10 to the minus 4. Then I still have this kind of, factor out of 1 over square root of 2. So this becomes just 1, 1. There's a negative sign as well from the negative charge. So then it looks like this becomes 9 times 10 to the 4 over 2 times the square root of 2. There's a negative sign, and 1 comma 1. Or if you want to think of it in terms of a unit vector, looks like this is 9 times 10 to the 4 all over 2. Negative 1 over the square root of 2, negative 1 over the square root of 2. 9 divided by 2 is 4.5, so it looks like this is 4.5 times 10 to the 4 newtons per coulomb. And then the unit vector, negative 1 over root 2, negative 1 over root 2. So that was fast, but you can always rewatch and try it on your own, which really is better than just rewatching. So then this is magnitude. This is your direction. Now again, I'm kind of factoring it in a way such that it's a magnitude times a unit vector, right? You can confirm that that vector I drew is a unit vector. Could you have also left it like that? Absolutely. I should use the laser pointer, right? This is also perfectly fine and correct, even though this is not a unit vector. But this is identical. It's like connected by equal signs to this. Either way is fine. So I could have written this, for example, as negative 4.5 all over the square root of 2 times 10 to the 4, 1 comma 1. Here are just kind of 9 divided by 2 is 4.5. Then I kind of left the square root of 2 as is, 10 to the 4, kept the negative sign up front. All of these are identical in saying that what magnitude is it? Here's the magnitude. And then what is the direction? Looks like it points to the left because it's negative in the x direction, and it points down because there's a negative in the y direction. And this vector, is equally pointing to the left as it is pointing down, which makes sense because we expected and a vector pointing with a 45-degree angle down. All right, before my computer explodes again, let me stop. So that's just for one charge, and then we'll kind of build. So notice that the math is more or less the same. We're just dividing one charge out. Conceptually, though, we've taken a giant leap forward in thinking about this concept of the field, that Q sub B creates this field everywhere around it that kind of specifies its existence.